All right. And then we will go back and we will run this. All right. So I'm going to be informal about this and just kind of do a walkthrough of some of the stuff here. I actually have a couple of visitors here. I think we have a site visit here. Welcome, Herbert. You can't see everybody who's here. We have some people with another group who are working in the lab space here doing other things. So there is some background noise. We share the space with a large number of people. It's a collaborative space here.
Great.
Okay,
yeah,
so this is the Bionic.
That space soon. I'm going to come check out the space soon.
I look forward to. We actually meet every Thursday, no later than 4:30 p.m.
Oh, okay.
And then we also meet on Saturdays, no later than 7:30 p.m.
Oh, okay.
I've got it to reverse. Thursdays, we've been able to wrangle time starting around 4:30 p.m. these days. So if you show up, there will be somebody here, and probably working. But everybody generally shows up no later than 7:30 on Thursdays. And then on Saturdays, we have an official start time of 4:30, but lately we've been able to wrangle start time of 2 o'clock.
On Saturday.
So we share the space with a large group of people, and we try and be unobtrusive and cooperative. And so that's why the schedule can be fuzzy.
You'll be meeting tomorrow?
We will be meeting tomorrow. And as I understand, okay, I plan on being here by 4:30 tomorrow. And of course, by the way, introducing myself, I'm Mark Miney, and I'm the team leader and the PI of the Bionic Leaf development kit project. So, and then actually here we have Herbert Sorrow, who's one of the team members. Hello. And a bioengineering faculty member, who's one of the founders, I think, of SoundBio and the prime movers. And then we also have our lab assistant here, Paul Schneckenberg, who is also a physicist as well. Stephanie is a physicist. So we have lots of physicists who are interested in this. Paul is our general lab magician and assistant, and does a lot of things. And he's here very often in the space and time that we have available. So he's also somebody, if you want to come in, get to know him and join us there. All right, so I'm going to go ahead and start walking through here. We have some people kind of coming in. I won't necessarily be able to introduce everybody as they come in, but we have a number of people. We have actually about a floating group of about 15 people now who come in at various times. Some of them are, we have 2 high school students.
Oh, wonderful.
Who are involved, and one of them actually is involved in 3-dimensional printing, which I'll talk about a little bit later. And then we have another group that's putting together our own electric gas sensors that we're going to build into the device eventually. So I'm going to go ahead. All right, so the Bionic Leaf Development Kit project. What's driving all of this, of course, is the unprecedented effect of increasing CO2 in the Earth's atmosphere, and that's leading to potentially catastrophic changes in the Earth's global mean temperature. And that I could run a course on that entirely all day today and convince you of that scientifically if you weren't inclined to be so. I won't do that. I'll just show you the classic graph. But of course, there are effects that are starting to be noticeable and undeniable. One is the intensification of storm weather that we've been seeing lately, and that there's a growing consensus among climate scientists and others that we're not causing more hurricanes, but the hurricanes we have are worse than anticipated. There are all sorts of other effects. I grew up and I have family down there who are in real estate. They know that the next bubble in real estate is because of the flooding that's occurring in Florida already, without having the huge increases in sea level that are predicted towards the end of the century, because Florida is unique. It's made out of limestone essentially, and the water percolates up from underneath. And so large areas of the southern part of the state are already unsellable from a real estate standpoint because they can't be insured reliably because of the periodic flooding that's already occurring. So we already have these effects now. And then there are other things that people haven't talked about very much. But as other people in other fields get involved, biologists in particular, there are other effects. One of my favorites is few people realize that photosynthesis, because of the nature of the enzymes involved in the photosynthetic process, actually shuts down after you have a 4-degree increase above the mean temperature we currently have. So if we blow past what the Paris Accords are already talking about, we run into the possibility that photosynthesis in general will decay or stop. And that's a physiological possibility. The other thing is that there's actual evidence now that as you increase carbon dioxide, you do have an increase in productivity short term for plant growth. But part of the problem with that is the crops actually decreases with increasing CO2. And so we now know that if you have a regimen where you have a very high CO2 level in the general atmosphere, even though it might contribute temporarily to greening, there are other effects that will occur later on that cause the crop growth to crash and also forests to crash. But they have lower nutritional value as well. So you're making lots of stuff that really is not really very useful from a standpoint of feeding people. And so that's another area that's interesting that, again, those are areas that people could be doing projects on that could be funded by crowdfunding and other short-term grants like the Amazon Cap and so forth that would be interesting for people to do as informal science learning, I think. Okay, so we can't keep the temperature from increasing by 2 degrees by mid-century, which was the original setting that the Paris Accord has, which most climatologists now agree that we've actually already blown past. And you can't do this without removing actively CO2 from the atmosphere. Simple emissions reduction is not going to be enough. And then here's the graph, of course, that explains that. And you'll be able to watch this, the information to the links to the graphs and data and so forth that I show. I'll post this after I process it on YouTube and post the link on the MEETUP site so you can review things and so forth. Okay, so to accomplish the goal of drawing down CO2 levels in the Earth's atmosphere to safer pre-industrial era levels, novel negative emissions technologies have to be developed and deployed. And one of those is the Bionic Leaf technology approach, which is typically a solar-powered hybrid electro-biomechanical device that performs what you could refer to as augmented photosynthesis. And some of the currently published attempts at doing this show that they're as much as 10 to 1,000 times more efficient and less resource intensive than biological photosynthesis. They don't use arable land.
This doesn't reduce CO2.
Yeah, it actually does. It removes CO2, makes it into products that either can be kept completely out of the carbon cycle.
Well, that's the only way to do it then. That's the only way to do it.
That's one way of doing it. Yeah, or you close the carbon cycle. There are two goals: either close the carbon cycle or reduce it completely by making things that don't put the CO2 back in the atmosphere.
What do you mean close the carbon cycle?
Well, for instance, if you make it into limestone, if you make it into plastics, then they're not going back up into the air. If you make it into fuel, like, say, methane, you burn it, but it burns clean to CO2 and water, and therefore there's a closed loop. So it can either make the cycle neutral, or if you're using it to make food and other things.
If you don't even make food and fuel, it has no effect whatsoever. If you just use it to do fuel and food, it has no effect whatsoever.
Well, it depends. There are a number of things. One of the things, for instance, if you do it to make food, yes, you eat the food and you burn it and you produce CO2. However, this technology allows you to make the food, say, on site in the middle of cities or in deserts or so forth. So that, in theory, could remove the emissions that would be generated, say, from transporting it or growing it by conventional things. Well, we can sit and we can go over some numbers later on if you'd like.
There can't be a net effect.
Why not?
The only net effect you get is the amount of food or fuel you keep in storage. It's the only net amount of CO2 you'll remove. But that won't be very much because you're using it all the time.
Conventional agriculture contributes about 40% of current CO2 emissions. If you reduce the emissions of conventional agriculture, that's what I'm doing. That's what I'm arguing. So even though the people eating the food will be generating CO2, the process of making the food and distributing it and so forth won't be generating CO2. So it has a net effect of negative emissions there. Okay. So anyway, so these can these negative emissions technologies have a promise for bringing about that kind of change. And then there are other things regarding this kind of biological augmented photochemical photosynthesis systems that you might find interesting later on regarding health and pollution issues that aren't related to removing CO2, but deal with other gases and other materials in the atmosphere that are affecting the condition of the human habitable biosphere, if you will. Okay, so we've been awarded a $100,000 grant from Amazon Catalyst to create a Bionic Leaf development kit, and our goal is to produce an open source kit that can be shared out over the internet and 3D printed for use in innovation. In other words, we're not going to make a kit that'll save the world, a device that'll save the world. We want to make a device that people connected to our group can download from the internet, build themselves in a do-it-yourself lab or a garage lab or what have you, and then tweak it, modify it on their own, and maybe improve it and come up with interesting possibilities. So kind of the model that I have in mind is like a development kit for software, except in this case it's a development kit for a Bionic Leaf, and so people can use that and start and do their own kind of innovation and development from that. It also can be used, if you want to start with the basic kit, that can be used for education purposes, for instance, to show students in high school or college or junior high school, for example, that in fact you can do this. And it's possible to do this sort of thing. And one of the motivators, two of the motivators actually on this is, one is an already available kit called the Mud Watt that Amazon actually sells, which makes electricity from bacteria that live in mud. Okay, and that's mainly a demonstration to show there is such a thing as bioelectricity generated by bacterial biofilms. And the other possibility there is the idea basically of that shows you, well, one of the classic kits that's available for sale is a simple kit where you place an actual green leaf in a container, and it has a simple CO2 infrared sensor, and you can show the decrease in the CO2 in the container generated by photosynthesis occurring in a leaf, and things like that. And so that could be a useful paradigm for this sort of thing from an educational standpoint.
You're explaining this because the person hasn't heard of this before.
I'm assuming that. Am I overdoing it, Stephanie, or underdoing it?
No, I'm just interested in general, so this is all interesting.
All right. Stephanie is a physicist.
Okay. I'll come back when
I'm almost there.
Oh, okay. All right.
Yes.
Okay, good.
So I'm almost through the boring part.
Okay, good. Yeah.
Herbert. Okay. All right. All right. So we're working on developing such a kit, and it now focuses on 8 specific modules. The first one, of course, is creation and acquisition of infrastructure for constructing the kit in the first place. That's things like getting scales to waste chemicals, getting the chemicals we need, doing things like building a do-it-yourself kind of fume hood, because there were concerns that we might be working with explosive gases like hydrogen and methane, and we'd like to have the ability to do that relatively safely. The next thing was the creation of an electrolytic device.
Number one is done then, is it?
That's effectively done, yeah. Creation of electrolytic device for CO2 harvesting, also coupled with hydrogen production that releases CO2 and H2 hydrogen into the bioreactor container for microbial conversion into methane. And we've essentially done some work that shows we've created a relatively simple electrolytic device that harvests CO2 from the ambient air and then pumps it out into our bioreactor, into any container we want to have it as a reservoir, pumps it out along with hydrogen, and those two can be used for anything. They can be used to feed microbes.
What does this do?
They can be.
Are you going to go through these in detail?
Yeah, I'm going to show you all of it.
All right.
Yeah, I could just jump ahead, but you know there are other people who haven't seen anything, and everybody's not as advanced as you are either. But you're going to miss it. I'm sorry, I'm going through this in a logical.
That's good. That's what you're going to do.
Yeah, but you're going to miss once I go through this. You're going to miss anyway. It's up to you. Okay. Okay. So the other is the development of electronic gas and other sensors, microbe selection and optimization, which we'll get started on soon. Growth and harvesting of the microbes produced in the bioreactor for use as fish food. One of our goals is to show that you can make food this way as well. And that has all the implications for agriculture and so forth that I mentioned earlier. Okay, developing, testing integrated prototypes. We're in the process of doing that. Implementing social media collaboration tools. This is part of that, doing the meetups. And one of the things, the fantasy world idea that I have is we'd like to be able to develop kind of the same kind of homebrew meetings for this that existed early in the IT industry, where we had people who had kits like this to tinker with and develop and learn from, and they'd get together and share that information either virtually on social media as we have it now, or in groups like here at Sound Bio, and then that would drive more innovation and development. And remember, VisiCalc, for instance, which basically made computers usable, came out of these, and this is where the Apple also came from. And so hopefully we can have something like that grow out of something of this sort. And then, of course, the final component will be implementing the solar power component. Right now, we're plugging everything into the wall, but we also have everything set. So we have a solar panel that powers a battery system that will provide all the electricity for the final device. So it will ultimately be solar powered in a true Bionic Leaf system. So those are the 8 modules. Ultimately, these will all be integrated into a single functioning device to be shared out for educational, innovative purposes. Okay, during the first 4 months of the project, this might be part of what Herbert would be interested in if he just wants to rejoin. So during the first 4 months of the project, we've built and deployed a simple but effective do-it-yourself fume hood, which we've been using. Okay, we've adapted a commercial gas analyzer to measure relevant gases for experiments. We've developed a series of homebrew gas analyzers. We're in the process of doing that to measure the relevant gases. And these are all store-bought components, and our hope is to build these kinds of sensors directly into the device. So literally you have a plus-minus go type system that tells you when you have the right gases and when you've harvested enough bacteria and methane and so forth and so on. I'll show you that shortly later on. Okay, we've created a novel hybrid electrolytic CO2 harvester, CO2 and H2 generator. And you can see here how we are able to generate hydrogen and CO2 from a simple electrolytic system and capture the gases and repurpose them into our bioreactor chamber. You can see from the control O2 measurements in the collection vessel that we're making more CO2 and hydrogen and not necessarily perturbing the O2 levels. That's a control. And then in addition, we are running some experiments that are kind of jury-rigged in a way. We're using some home kind of store-bought CO2 infrared sensors you keep on your desktop, which are adequate for our purposes, and showing that the electrolytic process we have actually draws down CO2 in the container. And so we can show that not only are we making CO2 from the ambient air and repurposing it into a bioreactor, I can show you that we're actually pulling CO2 out of the ambient air and reducing the amount of CO2 in this case in a container. Okay, so that'd be the same as putting that leaf in a bottle and having an infrared sensor for CO2 parts per million, and then shining light on the leaf and showing that the leaf actually removes CO2. So that's what we've got here. And we're in the process of doing more control experiments to convince ourselves that this is working this way. But we have a pretty good idea that it's probably working and will be a key component of all of this. Okay, and then of course we've constructed the phase 1.0 proof of concept device. And so we're just waiting on some difficulties we've had technically with our gas analyzer to move forward on that, but we have some really preliminary experimental data suggesting that when we add hydrogen to a container that has bug juice, that's a collection of microbes that is kind of our artificial wastewater, because many of the basic ideas and work that's been done on this are all using kind of a symbiotic mix of microbes and wastewater. And so what we've done is we've taken a compost that's made out of cow manure that is known to have methanogens in it, and then also septic tank bacteria and microbes. mixed together. And in the theory is that they will function to produce methane if we feed them hydrogen and CO2. And I'm going to show you data that's kind of, sort of, maybe okay at this point, but since we're among friends, I'll just show it. The basic gist of it is that if we feed the bug juice hydrogen, that is converted into methane. And this is really preliminary data, so don't take it too seriously. We've only done it once, and we were having some problems with our gas analyzer at that point, so we're not 100% sure.
Describe the axes.
So the first part of it is we're not adding any hydrogen. We have added CO2. There's a low baseline methane measurement already in the bioreactor as is. Now, we don't know whether that's because the sensors are malfunctioning or whether that's because that's real methane. That's part of the issue.
So the first two bars, one is 0. That's what you added.
That's right.
You didn't add any, because I can't read the writing here.
Oh, okay. Sorry about that.
Hydrogen, CO2,
and that's the methane you saw.
Right. So that's kind of the baseline. And then the next one, we add hydrogen directly into that mix, and then wait 24 hours and then take a reading. And I'm kind of summarizing smoothing over a lot of complications of the experiment. The hydrogen disappears. For whatever reason, we seem to have CO2 production and maintenance at this point in the bioreactor, which is interesting in and of itself. And then we have a slight increase in methane in this very first preliminary experiment.
You have a control.
Which kind of control are you asking for?
No CO2, no hydrogen, I guess.
Well, we can do that. That's one of the controls we can run. Yes.
Actually, I did do that effectively. Before we added anything, let's just let it sit for a couple of days and see what we saw.
Yeah.
Didn't see any.
No, you should put that up on the graph, because otherwise it's not convincing.
Okay, that's a good criticism, and I'll take that.
So you got a bit then, looks like.
So at this point, we have a preliminary methane signature with the caveat that we were having difficulties with our gas sensor at that point, and so I think
why are these CO2s? Why are they all maxed at the same level? Is that something?
Because the maximum amount we're reading is there's a set amount that the gas analyzer takes.
10,000 parts per million is the
max out
limit of the
sensor. Okay. Yeah. Until we can afford to have a gas chromatograph mass spectrometer and a technician to run it, that's probably the best that we can do at this point.
The biggest challenge is we don't really have a very good sensor.
We have a good enough
affordability versus what
we have kind of a good enough to get us going, but not an ideal situation. The ideal situation, like I said, would be the mass spectrometer gas chromatograph arrangement.
This is just one experiment. You haven't done any replicates.
We're in the process of setting that up.
We're struggling with the gas sensor.
Yeah, we actually
we're learning the realities of the gas sensor, the limitations.
Yeah. So this was just done last month, and so something else to keep in mind is we're a totally volunteer operation. So a lot of the work here, actually this whole experiment is Paul's work with very little input from other people, including me. And then the work that we've done with the drawdown work has been work done by Paul, myself, and one other person who's not here, Scott Mason.
It's a $100,000 project.
Well, it's also a shoestring project. So
I could do a little 100,000.
Huh?
I could do something with 100,000.
You could?
Yeah.
Let's see. Well,
I don't know about this.
First, and again, you have graduate students who have to show up every day and do something.
Yes.
I don't. I'm totally dependent on entertaining
but
people
you can show
enough
up
to come
every
here.
day.
Well, I live on the other side of the Sound. It's impossible for me to be here every day. Maybe if you bring up with me, let's wait until after the meeting and we can talk about it. Yeah, I suspect that there are issues
going on. This is a very formal
here.
meeting, is it?
This actually is for outsiders to kind of entice them to come and join us.
Okay, fair enough.
Yeah, so that was, fascinating.
When does the...
Another ambush. But anyways, sorry about that, Stephanie.
That's fine.
Anyways, sorry about that. All right. Anyways. All right. And of course, we're trying to make the video conferences and the on-site meetups like we're doing here as part of our social social system. So, all right. So here's how the device may look. This is kind of the cartoon version of it. We have the harvester system built into the basic reaction chamber like that, and then a red-green indicator system for carbon dioxide, hydrogen, oxygen, methane, and food. And so it's all powered by the solar-powered battery, and we have media and microbes in there. We start adding CO2 and hydrogen into the system, and goodbye.
You've got to show progress, right? And for 100,000, you should be able to show progress.
Okay, we'll talk about that later then. Thanks. Boy, I was surprised by that. Anyway, sorry about that, Stephanie. I apologize for that. All right. Okay. So anyways, these are the indicator lights. This is how it would run. And then the end point, of course, is we make food by measuring turbidity of the bacteria. We do, harvest the methane, and that can be used for fuel or advanced foods or plastics, as I mentioned, or harvest the microbes to make fish food. Okay, and then for updates, join us at our regular meetings once a month and via live video conference and things of that sort. And then here's our group of people. You saw Herbert here. Unfortunately, he stepped out. We have several other people who are here. Scott is away on a trip to Japan, and so he's not here, unfortunately, tonight. And we have other people who join us on a volunteer basis as time goes by. And of course, here are some of the other people who joined us and interact with us and have made contributions to the various parts of the project. Okay, so there's my contact information.
Okay.
Okay, and thanks. So any questions? And I do apologize. I didn't realize that I was getting an NIH or an NSF site visit.
That's okay. I mean, I'm flexible.
If you want to join us either virtually or whatever, you can join us on Slack. Just shoot me an email, and then I can add you to arrange to have you added to the Slack process. Okay. And that would be great. So any questions or anything like that? Or I hope we haven't scared you away. Things aren't normally this way.
No, absolutely not. Like, it's totally fine. Yeah, I think I'm really interested in being a part of the project. So it seems like it would be good for me to stop by and meet person to person.
Great. Yeah, well, if you want we are here tomorrow.
Yeah,
I know I'll be here by 4:30 tomorrow.
4:30?
Yes. All right. 4:30 tomorrow we're here, and any other time really. And if you want to come in at a time other than the regular Thursday and Saturday times, Paul and others are here at different times during that time. And I'm here also sometimes off the regular schedule as well. And you can just contact us about that, and be on a one-on-one basis kind of thing. Okay.
Then I'll plan to stop by tomorrow then. And
right.
You said this presentation is available.
I have to go ahead and process it and download it. Okay. I may not get to do that tonight.
That's okay.
I live due to circumstances that are very complex, I live on the other side of the Sound, and that limits the number of visits I can make each week. And so, and the time schedule. And so I may not be able to get this put together and download it until Sunday, but it will be available. And actually, if you want to write down my email address, you can shoot me an email there, and I'll get that. And then also there's a separate personal email that I also use. So you might want to send to both of these emails. Okay. The personal email is MARK at MEEMINY, that's MEMI, then N as in Nancy, IE.com. And if you send me emails at both of those addresses, I'll definitely get them.
Okay, so the second one you said is Mark at MEEMINY?
MEEMINY, that's MEMINIE.com.
Okay.
Yeah.
Great.
Okay.
Thank you.
All right. Yeah, thank you very much.
Yeah, I'm sorry I
Glad
couldn't
you
be there.
attended, and I apologize for the brouhaha.
No,
And
that's
things
okay.
aren't normally like that, and I apologize for not being prepared to deal with that properly.
Oh
So,
no, that's
but
great. And like I didn't expect, anything too catered to just me, so it's
okay.
totally fine.
Okay, well, you'll be visiting us tomorrow at around 4:30ish.
Yeah.
Okay, that
Perfect.
sounds great.
Great.
Yeah, all right. Well, great that you joined us, and we look
Yeah,
forward
thank
to
you so
seeing you
much.
tomorrow.
Okay,
And
have a
thank
great
you.
night.
You too. Bye.
Bye.
They had signs out, warning, traffic congested, chaos.